Hey, so I've got some new videos for you here, a new series, and these are all about angular momentum. Angular momentum, okay? Now, some things you need to know, just sort of generically as we get into this about angular momentum is everything you know about regular momentum is true for angular momentum as well, okay? Let me show you what I mean here. So with regular momentum, we know that the momentum we end with has to be equal to the momentum that we begin with, okay? As long as it doesn't get interfered with somehow, you know, that sort of thing. Same thing with angular momentum, okay? Angular momentum, which we use in H, same deal, okay? Linear momentum is a vector quantity, okay, like so. Angular momentum is a vector quantity, like so. Okay. Regular momentum depends on a mass and a velocity. Okay. So mv, just like this. Angular momentum also depends on a mass and a velocity. Okay. Now, here, however, is where they get different. Okay. Because angular momentum is actually a cross product between a location vector and the momentum vector. Okay, just like that. And so I'm going to do I'm going to do all these examples for you, so that'll make more sense. But okay, so far there we go. So what you end with is what you start with. That's true for linear and angular. They both depend on a mass and a velocity term. They're both vector quantities. Okay, and one other thing they have in common is the idea of impulse. Okay, so if we talk about a change in momentum, that's an impulse. And we said that that was an F dt. Okay, we can also talk about an angular impulse. All right, and that's going to be this, delta H. Okay, it's also an integral. Okay, but what we need is the rotational equivalent of a force, which is a moment. Okay, so we get m dt there. Okay, also a vector quantity. Now, typically we've done moments, normally we do them in in 2 dimensions, so m is almost always in the z direction, but it doesn't have to be. Okay, it doesn't have to be. And we've seen some examples of that in the past, like in statics, we did moments in 3 dimensions. Okay, so let's get to it here. We have this particle, okay, determine its angular momentum, h about at 0, all right, and so it's a bold h, that means it wants a vector, okay, about 0.0, that means that's going to be our location vector, okay, so we have to have a location vector, r. And so our location vector is going to go from here out to there. Okay, so there's R. And I'm going to write that down. R is, in this case, we go over 4, up 3. And I'm going to do this as if we're in 3 dimensions. Now, we're not. But when we get ready to calculate this thing, it's actually really helpful if you do it in 3 dimensions, which will make a lot more sense here in a second. Okay, the next thing that we need, by the way, I want to put the location for A here, is 430. Okay, we need the vector for the velocity. Okay, so it's at 10 meters per second, and we can see we got a 3, 4, 5 triangle there, so we got our bits. The easiest way to do that is going to be like this. Okay, that's supposed to be a V. All right, well, that's marginally better. So we got 10, and I'm going to go on to the x part, which is going as 3/5. Y part is 4/5 and 0. Okay. Now, you can multiply that 10 through if you want to. All right, doesn't really matter. I'm not going to, and that's because now I'm ready to calculate the angular momentum. Just that simple. Okay, so what I'm going to do then is I'm going to say that h about the origin is my location vector from the origin crossed with the momentum vector, all right, which is mv. Okay, and so what that does for me, I'm gonna go a long ways with this one. All right, what that does for me then is now I can say I've got 4, 3, 0 crossed with, whoops, it should be a cross, not an X. The mass, which in our case is 2 kilograms. The velocity, which is 10 meters per second, times the components of my velocity vector. 3/5, 4/5, 0. Okay, so there's my cross product. All right, now, if you have a Texas Instruments calculator, you probably have a way to execute that cross product. Okay, a lot of calculators do it. The calculator that I use on my iPad and my phone will do that, Calculator Infinity. There are lots of websites that have that capability, so you could just Google online cross product, and you're going to find a bunch of stuff. If you wanted to be really adventurous, you could figure out how to do it in Octave, which there's a command. Okay, what you have to do is you set up 2 vectors. I'll just show you real quick, like C and D, and then you just type cross C, D. That's your command, cross, just like that. So that's pretty easy to do if you want to pull out Octave. Okay, so now the way that I went about doing this, what I ended up with is I had the 2 times 10, and that gets me 20. So I've got 20. And then what I did with my cross product was I just used those 2 bits together. Okay, the 2 vector parts, I cross product. That sounds kind of stupid. I found the cross product of those. There's got to be a word for that, all right? What's the past tense of cross when you cross 2? Anyway, what we get there is 0, 0, 1.4. Just like that. Okay, and then what I would do is I would go ahead and multiply that through at that point. Okay, now our units on that are, let's check our units real quick. All right, so these are meters, kilograms, meters per second. Okay, so what I get this weird thing. It's a kilogram meter squared per second. And unfortunately, there's not really a good way to refer to that. Sometimes we could do this. Okay, we could do this. We could say kilogram meter squared per second squared times a second, which is a joule second. All right, that you don't see that very often. Okay, that's a pretty specific physics thing that you run into occasionally. I don't know that in your engineering that's going to matter. But so anyway, the bottom line is we're stuck with this nastiness. Okay, now one more thing we might do here is we might then go ahead all the way and say that H is 28Z. Okay, or sorry, I should probably put K. Oops, 28K kilogram meters squared per second. Okay, so that then becomes my answer. Okay, now I want to kind of take this and show you another one like super similar. All right, because you're going to have several of these kinds of things. They're not going to get more complicated. I do want to show you one more. I want to show you more of a true 3-dimensional type situation. So what we'll do, we'll just kind of like go boop. Okay, and I'm going to make a 3-dimensional, system here. All right, marginally better. Okay, X, Y, and Z is up, of course. And let's put our point A over here, but let's put it off of the XY plane. Okay, so I'm going to put it in the same basic XY location, but let's just put it up 2 meters. Okay, and then let's have a point over here. We'll call it B, and B is going to be minus 2, 0, 0. So B is on the x-axis there. Okay, so X, Y, Z. All right, so it's there. All right, now what I want to show you how to do is to find the angular momentum if we're not on the origin. Okay, so that was supposed to be a B. Didn't really turn out very well. Oh, that's better. I feel better about that. Okay, so we follow the same basic plan, which is we need a location vector, all right, and then we need the velocity vector. So our location vector this time, I'm going to call it R sub B, is there. Okay, and so R sub B, all right, in terms of X, all right, we go forward up to 0, 2, and then 4 more, so we go forward 6, and then still 3 and 2 is fine right there. Okay, just like that. Now the velocity vector, I don't want to change that. I'm going to stay with the same velocity vector. Okay, 3/5, 4/5, 0. Okay, so all that remains the same. Now let's find the angular momentum about the point B. So we'll have RB crossed with MV. Okay, and so we put in our R value, 6, 3, 2. We're going to cross that with 2. That's our mass times the 10. And then here's our vector notation, 3/5, 4/5, 0. Okay. Now, once you do that, what you end up with is we still have the 20 out front, but the cross product of the two vector bits is different. So we get minus 1.6, comma 1.2, comma 3. All right, and we still have this unusual set of units. Okay, so again, meters, kilograms, meters per second. All right, that sort of thing there. So now if we distribute the 20, what we end up with is minus 32, 24, and 60 kilogram meter square per second. Okay, and so, we could talk about the different components of that angular momentum. All right, so in this case, we've got an X component, a Y component, and a Z component. All right, and so it might be important for some application to know what the component was, this direction or that direction, that sort of thing. Okay, just treat it like a regular vector, and it's good to go there. Okay, now the one thing I want to show you, let me point out one more thing, then we'll call this one good. Thing I want to show you is we had the same velocity vector here and here. Okay, but we got very different answers for angular momentum. All right, that's one place that the linear momentum and the angular momentum are very different. Okay, because the linear momentum does not depend on where you are. Okay, where you're talking about. Okay, it is. Okay, so until you're talking about something going fast enough to make it have to be treated as a relativistic particle. But anyway, it doesn't matter where you are. Even then, it doesn't matter where you are. Okay, but with H, it matters where you are. Okay, just like this. And so that provides challenges and opportunities. Okay, and we'll see some of those as we move along. All right, well, that first video got just a little bit long-winded there. I apologize, but I covered a lot of ground for you there.